Keep pushing you away while I want you to stay. Amazing cold as ice, but my heart still beats. When I say no, it's yes. I'm putting you to the test. Can you handle me? Do you have the key? Sorry that I've been playing games. Do you really have what it takes? I guess so, I guess so.
The min cut problem. Okay, so we talked about max cut. Let's now talk about min cut. And it's basically the same problem, but we're trying to now minimize the number of cut edges rather than maximize the number of cut edges. Okay, so here I'm going to assume that we start with a connected graph. That just is a bit more convenient to assume that the graph is connected to begin with. And now we want to find a subset of the vertices once again, such that the number of edges from S to V minus S is now minimized. And I'm going to assume that, of course, because it's a minimization problem, I'm not going to allow you to just pick an empty set or S to be the whole vertex set V. So like we want a non-trivial cut here. Okay. And yeah, so this is the min cut problem. Why is the min cut problem interesting? Well, it's like it gives you a notion or a measure of how connected your graph is. So if you have a min cut value of, let's say, 0, let's say we didn't assume the graph is connected. If the min cut value is 0, then that's a disconnected graph. It's not a connected graph. If the min cut value is 1, so then you're saying that I can, partition the vertex set into two parts such that there's exactly one edge between them. That means that I can remove one edge from the graph so that I disconnect the graph. Right? By removing one edge, I can disconnect the graph if the min cut value is 1. If the min cut value in general is k, then that means that I can remove k edges from the graph such that the graph is disconnected. Okay? And in most applications, you want graphs that have high min cut value, right? So you want graphs to be sort of like well connected in that sense, so that even if some of the edges fail, you still get a connected graph. You still have a connected graph. Okay. Now, you might think that the min cut problem, just like the max cut problem, is NP hard, but actually it is polynomial time solvable. Okay, so there's an algorithm that solves min cut in polynomial time. And yeah, I'm pretty sure that this would be something that you see in 451, this algorithm. And what we're going to do here is actually not see that algorithm, but we're going to look at a simpler, in some sense, a simpler and elegant randomized algorithm for min cut. Okay. Now I'm going to show you a Monte Carlo algorithm for min cut. This is called the contraction algorithm. Okay. And I'm going to demonstrate this algorithm to you by doing an example run, and then you're going to understand how it works. It goes iteration by iteration. At every iteration, we do the same thing, so it's going to be relatively easy to understand what goes on. Here's my example graph, and I'm giving you actually like 2 copies of the graph because as the algorithm proceeds, I'm going to actually modify the graph. So on the right-hand side here, I'm going to keep this as is. So you have a reference for the original graph that we started with, and I'm going to modify this other graph as the algorithm proceeds. Okay. Now, before I begin with the algorithm, what is the min cut value for this graph? Size of the min cut? Well, you can expect this, and you'll see that basically the size of min cut is 2. Okay, so you can put like E, the vertex E on one side and every other vertex on the other side. So you get a cut of size 2. And by inspection also, you can see that you can't get a cut of size 1 in this graph. So the min cut value is 2. Okay, so now let me show you this contraction algorithm. So the way it's gonna work is that we're going to select an edge randomly. Okay, so randomized algorithm. Uniformly at random, select one of the edges. Okay, and maybe that edge might be the BD edge here. That's the green edge, BD edge. Now you have B, you have D, and what we're going to do is call the contraction algorithm because, the main operation in the algorithm is a contraction operation. And what that means is basically you take those 2 vertices and you merge them together. Okay, you merge them to B and D together here so that they become a single vertex. Okay, and then sort of you update the edge structure. Okay, and the green edge here, the BD edge, is going to become a self loop when you merge B and D together. Okay, That self loop we're going to get rid of. We don't care about self loops. They don't matter. But then we're going to keep all the other edges intact. We're not going to touch them. Okay, so if you contract this edge, this is what happens. Okay, B and D comes together. Every other edge is there, but the green edge, the original BD edge, became a self loop, and we just threw it out. Okay, throw out, delete self loops in this process. And this is one iteration of the algorithm, and this is all you do. Okay, so you just keep repeating this operation over and over again. Okay, so next iteration, select an edge randomly. Maybe now you select the purple edge, which corresponds to really picking the A vertex and the BD vertex. Now B and D, the vertices B and D merged and formed one single vertex now. So BD is a single vertex. Now we contract, like we merge them, right? And then now there are two edges between A and BD. There's the purple edge and there's the black edge. Those will become self loops, and then we're going to throw them out. Okay, so watch it happen now here. A merges with B and D. The purple and the black edge became self loops. We threw them out, and then this is the resulting graph. Good. Repeat, right? So now we select another edge at random. Maybe the blue edge is selected now. So we merge the vertex C with the vertex ABD. We merge them together, delete the self loops, and then this is what we end up with. And now this is the stopping condition. The stopping condition is when you have two vertices left in the graph. Once you have two vertices left in the graph, that's basically corresponds to a cut, and that's the cut that you output. So in this case, on the one side of the cut, we have the vertices A, B, C, D. On the other side of the cut, we have the vertex E, and that is exactly in the original graph, it corresponds to this cut here, right? And that is what we do. When two vertices remain, you have your cut. S is going to be A, B, C, D here, and V minus S is E, and the size is going to be here too. We actually found the min cut in this particular case. Now, of course, this is randomized algorithm, so maybe we got lucky here, we found the min cut, but maybe if we run it again, it's gonna give a different output, right? So let's say again, let me do another run now, example run number 2. The green edge is again selected, BD, you merge them together, and we have the same situation as before. But now imagine at this second iteration that the yellow edge is selected. Okay, so now we're gonna merge BD with E. Okay, so now those yellow and gray edges became self loops. You throw them out and they're gone. And now you can see like I won't be able to output that minimum cut anymore. Anyway, so we continue. We select maybe the red edge here. So we merge C with BED. And then at the end, we have two vertices left. This is the stopping condition, right? So this is now corresponding to the cut where S is like, let's say the vertex A, and V minus S is all the rest of the vertices, B, C, D, E. Okay. And when two vertices remain, you have your cut. We're here, S is A, and V minus S is B, C, D, E. And in this case, now you see that the cut value is actually 3. So we are sad. We did not find the min cut in this case. Let's now, first of all, look at the number of iterations of the algorithm. Who can tell me how many times this algorithm is going to repeat? Really, like we start with the original graph, and what are we doing, right? I mean, every time we contract an edge, we're taking two vertices and merging them together, which means effectively the number of vertices is being reduced exactly by 1, right? That's what happens. When you merge two vertices together, the number of vertices in the whole graph is reduced exactly by 1. Right, so we start with G0, which is the original graph. So I'm going to denote by G sub I the graph that we have, okay, after I contractions, okay, after I iterations. And as we said, right, the number of vertices, as I said, it goes down by exactly by 1 at each iteration because we're merging two vertices at each iteration. We stop when there are two vertices left, so that means we have n minus 2 iterations for that reason. Now the iterations here, I'm going to label them or index them, I should say, as follows. Like the first iteration, I'm going to think of it as iteration 0. The second iteration, I'm going to think of it as iteration 1, all the way up to iteration n-3. That's going to be a convenient indexing when I do the analysis of the algorithm. So something to keep in mind. Okay, so that's one observation, n-2 iterations, and a contraction operation can be done in polynomial time, obviously. So the overall, this is a polynomial time algorithm. But now the question, one important question, I guess, is we are outputting basically a cut in the last graph, right? In graph G sub n-2. Does that correspond to a cut in the original graph G? And it's not hard to see. It's kind of like an observation, but the answer is yes. And in fact, like for any I, no matter what GI you're looking at, a cut in the graph G sub I, after I contractions, of a certain size k corresponds exactly to a cut in your original graph G of size k, okay? And so like you can see this like as an example, here is like say some G sub I, you've done some contractions, and let's say you said, okay, let me stop here and like let me identify a cut in G sub I, and maybe it's still like the one that's shown here. Well, you know, the claim is that the same cut is there in the original graph G. And the way, I think a nice way to see this is that, you know, if you imagine taking these vertices that were contracted, merge, and uncontract them, right? So in this case, for example, B and D, B, E, D are merged together. If you imagine uncontracting them, like undoing what the algorithm has done, then you'll see like, okay, so those edges between B, E, and D are gonna appear again here, but they were not even part of they're not part of the cut anyway, so they don't really matter. And the original edges, like the black, purple, orange, red, all those ones remain, of course. That doesn't affect anything, right? So if you imagine in your mind, like uncontracting, of course, like all the edges that go across, they're gonna still be there, and you have the same cut. And so like when we do again with G n-2 at the end, like two vertices left, and this is the graph that we have. Once again, you can imagine like uncontracting both sides of the cut, and sort of those edges between the vertices in the S set and between the vertices in the V minus S set, they start appearing, but they don't matter anyway. And the edges that go across, they are there. Okay. So that's an observation that is important. And now it's time for me to tell you what performance does this algorithm have? What is the success probability? Okay, so here's the theorem. The theorem is that let G be a graph with n vertices, then the probability that the contraction algorithm outputs a minimum cut is at least 1 over n squared. Okay, that's the theorem. Now, you might say like, I mean, should I be impressed by that? Because this is not an error probability, it's a success probability, okay? So if you're telling me like, oh, I have like 1,000 vertices, n is 1,000, then my success probability is 1 in a million, 1 over a million. If you have 1,000,000 vertices, you know, it's even much, much worse, right? So it's very close to 0. So what are we doing here, right? You know, this seems like a very bad algorithm on the surface of it. On the other hand, that would be the wrong impression, okay? So let me try to convince you that this is actually a very good algorithm. So first of all, it runs in polynomial time, which is a good thing, of course, but you know, that's not the reason why you should be impressed, of course, because there are lots of polynomial time algorithms that have poor performance, possibly. So let's come back to this observation that we made before. There are exponentially many cuts in the graph, and if you were to just pick a random cut uniformly at random, your success probability would be exponentially small. And this algorithm is giving you success probability not exponentially small, but only polynomially small, 1 over n squared. So this is actually doing something much, much better than just randomly picking a cut. Okay, so there's something really non-trivial going on here that makes the success probability 1 over polynomially small rather than exponentially small. And the key point now is that the success probability is large enough so that I can actually boost it up to as close to 1 as I want, okay? We can boost the success probability to something like 1 minus 1 over e to the n, 1 minus exponentially small, and still remain in polynomial time, okay? This is what I would call 1 over n squared success probability, or in general, a success probability, which is 1 over a polynomial in n, is in some sense a boostable success probability. Okay, and we're going to see that. I won't tell you now how, but later I will show you how to do that. But the point is that this is just good enough that I can do something with it to boost this up to close to 1. Okay, so, and then we're going to do that. So now, two things we're going to do in the remaining of the lecture is basically, first, I want to prove to you this theorem. Okay, so first of all, let's see how you prove that. And then two, I'm going to show you how to do the boosting phase. Okay, and so get to a probability, success probability, very close to 1. Okay, good. So now we're going to do the proof of a theorem, and we're going to actually start with a poll here. Okay, because I want to this is an observation that's going to be important, an important part of the proof. So let's start with this poll. So I'm going to open the poll in a second, but let me just first read what the question is. Okay, let K be the size of a minimum cut. Okay, and I want to know which ones are true. So I want to know the relationship between the size of a minimum cut K and the minimum degree in the graph. Okay, so in the original graph, how does K compare to the minimum degree? And also for every, G sub I, after every contraction, G sub I, how does the size of a minimum cut compare to the degree, minimum degree of the graph? Let's look at the poll answer. Okay, and the answer is basically that the minimum size of a minimum cut, basically K, is upper bounded by the minimum degree. And it doesn't matter which graph you're looking at, it's initial graph or after I iterations, this is the relationship we have. Another way to say this is to say that, for all G sub I and for all vertices in that graph, the size of the minimum cut is upper bounded by the degree of the vertex. Okay, for any vertex, the degree of a vertex upper bounds the size of a minimum cut. Now, it's definitely not going to be the case. Like again, just keep in mind this example of Kn over 2, Kn over 2, right, joined by a single edge. So now here, of course, K is equal to 1, right? And the minimum degree, on the other hand, is about n over 2. So it's definitely not going to be the case that the minimum degree is lower bound on the size of the cut. But the other relation, so K is not going to be more than the minimum degree, but it is going to be the case that K is upper bounded by the degree. And what is like the simple maybe explanation, like a one sentence, in some sense, justification for this? What would you say? We can always just pick the vertex with lowest degree, right? Yeah, exactly. So, a single vertex V forms a cut of size degree of V, okay? So that's really the crux of the argument, right? So example, let's say you're in some G sub I, doesn't matter which one it is. Take, let's say, some vertex A, V, in this case A. That forms, if I just now look at the cut formed by putting A on one side of the partition and everything else on the other side, then I get a cut. I induce a cut whose size is exactly the degree of the vertex, right? There's a cut of size for every vertex A, V, there's a cut of size, the degree of that vertex, okay? And as we observed before, same cut exists in the original graph, right? And so then, of course, that means K is upper bounded by the degree of that vertex, in this case 3. Why? Because K by definition is the size of the minimum cut, right? So it can be better, there might be a better cut in the graph, which has size smaller potentially, but it's certainly not going to be worse than this particular cut that we have demonstrated here, okay? So for every vertex phi, the degree of the vertex, is a potential, it's a cut, it corresponds to a cut with that value. So the size of the minimum cut is of course going to be at most that value. It could be much better. Good, so now we're going to make use of this. Okay, so let's put it up there. All right, so observation 1, for all GI and for all vertices V in GI, K is upper bounded by the degree of the vertex. And this is the theorem that we're going to prove now. The probability that the algorithm outputs a minimum cut is at least 1 over n squared. Now, you can stand up, stretch a little bit, get ready for this proof, okay? So it's going to take us like 20-25 minutes. It's going to be like, you know, pretty spicy proof, quite involved, multiple steps going on. So yeah, you know, get ready for it, you know, try to concentrate for the next 20-25 minutes. I promise you it's a very nice proof, okay? So it's like very, very cute, very nice analysis. And at the end, everything's going to work out very beautifully, okay? All right, so let's do it. So I'm going to start by fixing some minimum cut, okay? So, and I'm going to view the cut as a subset of the edges. So let's say we fix some minimum cut, you know, one side of the partition is S, the other side is V minus S. There's some edges between S, there's some edges between V minus S, and then there are the cut edges. And those edges in the cut, those edges that go across, I'm going to call that set of edges F. And F, I'm going to think of as the minimum cut here, as the cut, okay? Now, some notation. K is going to be denoting the size of the minimum cut, this particular cut, which is the number of edges, right? So this is the number, the size of F. I'm going to denote by n sub I the number of vertices in the graph G sub I. G sub I is the graph after I iterations, after I contractions. And I actually know what exactly n sub I is going to be with respect to n, which is like the number of vertices in the original graph. As we said, in each iteration, what are we doing? Well, the number of vertices goes down by exactly 1, right? So it's going to be n minus I. Yes. Exactly. So then n sub I, number of vertices in G sub I, is going to be n minus I, exactly. And similarly, we're going to denote by m sub I the number of edges in G sub I. Now, I could ask again, well, what is m sub I equal to with respect to the original number of edges m? And there, well, we don't know, right? We don't know how the number of edges evolves over time as the algorithm proceeds. You might, you know, get rid of a lot of edges in one iteration. You might not get rid of too many edges. We don't know. And this is going to be actually important. The fact that we don't know how the number of edges evolves over time is going to actually inform how we do the analysis here. And you'll see where it comes into the picture. But this will be actually an important fact that we don't know how the number of edges evolves, but we do know how the number of vertices evolves. Good. Now, the probability that I'm interested in is the probability that the algorithm outputs a minimum cut, right? And this is lower bounded by the probability that the algorithm outputs this particular min cut that I fixed, outputs F, okay? Now, this could be, the inequality here could be an equality if there's exactly one minimum cut in the graph. So, and I'm fixing it, my minimum cut to that minimum cut, and then this would be an equality. But in general, of course, there could be multiple minimum cuts in the graph. And I'm only looking at one fixed minimum cut, and I'm only gonna look at the probability that I output that particular minimum cut. So, of course, the probability of success in general could be higher because I could be outputting some other minimum cut, but that's okay. I'm not going to worry about this. I'm going to fix a particular minimum cut, and I'm going to look at the probability that I output that particular minimum cut. And my task is going to be now to lower bound this probability that the algorithm outputs F by 1 over n squared. Okay, so we want to show that this probability is going to be at least 1 over n squared. Good. Now, what does it mean for the algorithm to output F? So now I want to get like a convenient representation or a convenient understanding of what it means for the algorithm to output F. So this is my question to you now. What do you think? The algorithm outputs this particular minimum cut f if and only if what? Like, what could be like a nice characterization in terms of what the algorithm does? Yeah, exactly. Okay, so you guys have it. Never picks an edge that's in f. Okay, so this is the observation. If and only if it never contracts an edge in f to contract. So why is this the case? So let's look at it from the perspective of this guy here. Okay, so what I need to argue to you is that if the algorithm never contracts an edge in f, then it will output f. And second, if it does contract an edge in f, then it cannot output f, right? So if I make those two arguments, then you'll see that this is correct, right? So let's start with the second one, right? So suppose that the algorithm actually does contract an edge in f. Okay, so what does that mean? So maybe it picks this edge here in f, and it's going to contract that. Well, if you contract that edge, what happens? That edge is going to become a self loop. And when it becomes a self loop, we remove it, right? And so you're not going to be able to output that cut anymore, right? So if you contract an edge in f, that becomes a self loop, you throw it out, and you won't be able to output this cut f. So that's the easier maybe direction. But the other direction is also pretty straightforward. So suppose now it never contracts an edge in f. Then does it output f? And the claim is yes. Why? Because suppose you're never contracting an edge in f. What does that mean? Then it means you're going to be contracting edges within s, either within s, or you're going to be contracting edges within v minus s, right? You're never going to contract an edge that goes across s to v minus s. So you're going to keep contracting edges in s, and you're going to keep contracting edges v minus s. And then when does the algorithm stop? When two vertices remain, right? So that means that the vertices in S are going to merge into a single vertex. The vertices in V minus S, they're going to contract into a single vertex. And then you're going to stop there. And then you're going to output exactly the cut, exactly the edges that go across S to V minus S. Hopefully you follow that. But if you did not, that's okay. You can think about this offline a bit more to convince yourself. Don't get stuck on that step. Just for now, take this observation as is. Believe that it's true. You can come back to it later if you want. All right, now that means I can write my probability of success, the algorithm outputs f, as the probability that the algorithm never contracts an edge in f. Okay, now I want to write this probability, algorithm never contracts an edge in f, in a convenient way. And usually when you have an algorithm that goes iteration by iteration, it's a nice idea. It's usually a good idea to break it up, based on the iterations. So what's going on in each iteration? So we can actually write this. Let's create this event E sub I to be the event that the algorithm does not contract an edge in f at iteration I, right? And so now with this definition, it will allow us to write this nicely as the probability that the algorithm does not contract an edge in f is the probability that it does not contract an edge in f in the first iteration, it does not contract an edge in f in the second iteration, and it does not contract an edge in f in the third iteration, and so on. Right, so that corresponds to basically this event that I've written here, E0, intersection E1, and E2, and E3, and so on. Okay, now when you have something like this, the first thing you would ask is what? Like we say, okay, I need to analyze this. Are the events independent? If they're independent events, then I can write this as a product of the probabilities of these events. And are they independent? If I don't contract an edge from f in the first iteration, good, yeah. No, exactly, I agree, right? So if I don't contract an edge from f in the first iteration, then that will make it more likely in the second iteration that I will pick an edge from f to contract in the second iteration, right? You guys are right, so it's not independent. Sorry, doesn't work. But what can we do instead then? What can we do instead? If in this kind of situation, I mean, there's only one thing really sort of pretty much left to do. You cannot use independence. you're gonna use chain rule, right? Exactly. So we're gonna write this as probability that E0 times the probability of E1 given E0 has happened times probability of E2 given E0 and in E1 has happened, and so on. Right, so that's the chain rule. You can always do this. The events here don't have to be independent for this one. And now you have this, right? And we have to analyze this. We have to lower bound this. And this kind of looks scary, right? Because like, well, I mean, how can I analyze probability that E2 given E0 and E1 and so on and so forth? It doesn't look tractable, but it is. Okay, so we are actually going to be able to go through these one by one in some sense and lower bound each term here. And we're going to see that actually the analysis is the same for each one. Okay, so let's do that. Let's go one by one. We'll start with probability of E0. So this is the probability that we do not contract an edge in F in the 0th iteration, I should say. And let's look at it from the complement, right? So this is 1 minus the probability of the complement of the event, which means now I want to know what is the probability that I do contract an edge in F in the 0th iteration. And what is that probability? Okay, well, we have the original graph here, right? Right, we have all this. So you can imagine you have a bag. All the edges are put in the bag. And some of those edges are the F edges, and I'm basically picking randomly one of those edges out from the bag, and I want to know what is the probability that I will get a cut edge, right? F, an edge from F, right? Right, so you guys have it. So this is basically the number of edges in F divided by the total number of edges in the original graph G, right? So that is, of course, 1 in our notation. That's going to be 1 minus K over M0, right? M0 is the total number of edges in the original graph, and K is the number of edges in F. Good, so that's equality. Now let's do now the second term. What's the probability that we do not contract an edge in the first iteration, given that we did not contract an edge in the 0th iteration? Okay, and we'll do the same trick, right? Right, in terms of the complement. 1 minus probability of the complement of E1 given E0. So now I want to know what is the probability that I will pick an edge from F to contract in the first iteration, given that I did not pick an edge from F to contract in the 0th iteration. Right? Okay, so now I still have all, which means like assuming, conditioning on E0, conditioning on the fact that I did not pick an edge from F to contract, all those edges from F are still in my bag, right? And the total now number of edges that I have, it's not M0, but it's going to be M1, right? So now I have a bag with M1 edges in total. I still have all the edges from F in the bag because we're conditioning on the fact that we did not contract an edge from F. I'm picking one at random. So again, the success probability or the probability here is going to be K over M1, right? So all those K edges remain in the bag, but now the number of edges I have in total is M1, not M0 anymore. So it's basically the same, but instead of M0, it's M1. And in general, of course, the analysis, hopefully you agree that the analysis is going to be the same, right? So in general, the only thing that will be different is, what I am picking. So the ith term here is going to be equal to 1 minus K over M sub I. Okay? All right, so now comes in some sense, the creative part of the proof, because this is great. This is a very nice expression in some sense for the ith term, 1 minus K over Mi. But the problem is, which I highlighted before to you, is that we don't know what Mi is, M sub I is. We don't know how this evolves. Okay, so this is where now we have to be a bit more creative to give this, write this expression in a form that we know we can control in some sense. And the idea here is going to be to try to write m sub I in terms of n sub I, which we know what it is, and k. And hopefully, like when we write m sub mi in terms of ni and k, maybe the k is also going to cancel out, so that maybe we're going to get something just in terms of n sub I, which we have full control over, like we know exactly what that is. Okay, so now we have the important terms here are the number of edges, number of vertices, and k. So, but k we know. Let's now go all the way back to the beginning, right? So observation 1, k is upper bounded by degrees, right? Minimum degree. So now you have something involving degrees of vertices, edges, and number of edges and number of vertices. So what should we try to use? What does this remind you? If we have number of edges, number of vertices, degrees of vertices, what can we try to use here to relate these quantities? Yes, handshake. Let's do that. Here's the lemma now that's going to use, and we're going to prove this using the handshake lemma, okay? So my claim to you is that 2 times mi is lower bounded by k times n sub I, okay? And maybe you kind of already see the proof here. But before I tell you the proof, let me just rewrite this. Okay, so this means just by rearranging the terms that k over mi is upper bounded by 2 over n sub I. Okay, that the second part is just rearranging terms. Why I want to write it this way? Because I have k over mi here. The ith term is bounded by k over mi, and so I want to write it in terms of k over mi. All right, so that's the lemma we're going to use. Let me now show you quickly the proof, right? And the proof is basically the handshake lemma, okay? So we know by the handshake lemma that the sum of the degrees of the vertices is equal to 2 times the number of edges, right? And this holds for multigraphs as well, okay? So maybe like a small comment there is that we have multigraphs here, and the same proof for handshake lemma will go through for multigraphs as well. Nothing changes. So we have this. And then on the other side, of course, by observation, we know that the degree of any vertex, degree, is lower bounded by k for every v, for every vertex, right? So I can lower bound this whole sum by k times n sub I, right? So the number of vertices I have. Now, number of terms I have in the sum is n sub I. And each term here is lower bounded by k, so I have the lower bound k times n sub I. Okay? And then you get the result that we want. That's the proof of the lemma. K times n sub I on the one side, 2 times mi on the other side. All right, so we have that. And now what does that mean? Now that was the proof, but now let's put the lemma here and bound the ith term, right? What's the ith term is going to be bounded by? The ith term is bounded by 1 minus 2 over ni, because k over mi is bounded by 2 over n sub I. And I know exactly what n sub I is, right? So I'm going to disappear now for a while. So I have room here. We know what n sub I is. It's n minus I. So this is exactly 1 minus 2 over n minus I. And I can write this actually as n minus I minus 2 divided by n minus I. Why? Because I can just view this one as like n minus I over n minus I. If you view that as that, then you see it, right? So now we have that. The ith term is bounded by that. And now we're clear for takeoff, okay? So now we're ready to go. We're ready to finish the proof. Because why? We know now that the probability that the algorithm outputs f is the product of these terms, the 0th term, the first term, second term, third term, and we have a bound on each of these terms, right? So when I is equal to 0, the bound we have is n minus 2 divided by n. When I is equal to 1, it is n minus 3 divided by n minus 1. When I is equal to 2, it is n minus 4 divided by n minus 2, and so on. So we keep going like this until we hit 2 over 4 and 1 over 3. And then the math gods are nice to you, right? Because massive cancellation. The n minus 2 upstairs, n minus 2 downstairs, they cancel each other out. N minus 3 upstairs cancels n minus 3 downstairs, n minus 4 upstairs cancels n minus 4 downstairs, and so on and so forth, until there are 2 terms of, in the numerator remaining and 2 terms at the bottom remaining. So you get 2 over n times n minus 1, which is exactly 1 over n choose 2, right? This is the reciprocal of n choose 2. And n choose 2 can be bounded by n squared. N squared is a bigger quantity, so this is lower bounded by n squared. And there we go. We have the proof. Okay, fireworks. And we did it. So that is satisfying, right? I mean, I think that's a very nice, cute proof and a very nice analysis. Really, I think the creative part here is, again, like using the handshake lemma to write basically this k over mi term in terms of just n sub I. But otherwise, all the other steps are pretty much forced, I think, and it's pretty standard, I would say. We have a Monte Carlo algorithm with error probability at most 1 minus 1 over n squared, or the success probability is 1 over n squared. And now I want to talk to you about the boosting phase, right? We can boost the success probability to arbitrarily close to 1. In other words, I can lower the error probability to 1 over e to the n. Okay, I can lower the error probability and make it as small as 1 over e to the n, from an error probability of 1 minus 1 over n squared. And what do you think the idea is going to be now? It's going to be the boosting phase, and I'm going to show you the world's greatest inequality. What's the idea? What should we do? Yeah, run it over and over again. The main idea here is run the algorithm independently t times using fresh random bits, right? So I'm going to run it once, get some cut f1. I'm going to run it again, get another cut f2. I'm going to run it again, get another cut f3. I'm going to run it again. I'm going to do this t times, okay? That will produce t cuts for me. And among those t cuts, I'm going to, of course, pick the one that has the minimum size. Output the minimum among the fi's. That's the algorithm. That's the idea, right? And I hope you agree that, you know, as I make t larger and larger, my success probability is going to get better and better, right? Because I have like more tries to get to the minimum cut, to find the minimum cut. So the question really is, what is the relationship between the number of repetitions here that I make and the success probability? Or in other, equivalently, what's the relationship between t and the error probability? And actually, I'm going to look at the error probability. I'm going to upper bound the error probability. And recall, our goal really is to upper bound the error probability by 1 over e to the n, right? I want to show that the error probability is at most 1 over e to the n. Okay, and I'm going to pick t accordingly. I'm going to pick the t that makes that happen. So how can I do this? So the probability of error is the probability that we don't find a min cut. And again, I'm going to break this up into different repetitions, right? Like, why not? So AI is going to denote the event that in the ith repetition, we don't find a minimum cut. Okay, so then we're going to write this probability of error as we don't find a minimum cut in the first repetition, we don't find a minimum cut in the second repetition, and so on. Like, so that's the why we get ands of these things, or the intersections of these events. Now I ask you, are these independent? Does one repetition affect what happens in on another repetition here? Right? No, right? Doesn't matter at all. I mean, you can run these in parallel if you want. Okay? Right? So these are independent runs. You can run them in parallel. One won't affect the other. And yeah, so we can write this now as the product of the probabilities. Very good. All right, so we have that. Now, is the probability of A1 different from probability of A2? Of course not. I'm doing exactly the same thing at each repetition. So this is really the probability of A1 to the power t. And T, and here I'm happy. Like I'm smiling here when I see this. Why? Because I see the exponent, I see T in the exponent. Okay, when I see T in the exponent, I'm smiling because now this is decaying exponentially in T in some sense. So let's now rewrite this, right? The probability of error now, I can write it as the probability of A1 to the power T, but I know what's the probability of A1. What's the probability that in one iteration, I give the wrong answer? Well, in one iteration, I give the wrong answer with probability 1 minus 1 over n squared, right? So I have 1 minus 1 over n squared to the power T. And now you might be like, oh my God, how do you like analyze this? How do you bound this? This looks ugly. But here is where we're going to now use the world's greatest inequality. The world's greatest inequality is something you've seen before in recitation last week. For all x, 1 plus x is upper bounded by e to the x. Okay, for all x, 1 plus x is upper bounded by e to the x. The proof, you want to see the proof? Here is the proof. Okay, so here is e to the x and 1 plus x, and you can see the e to the x line is above 1 plus x line, and so that's it. Okay, that's the proof. And you can see like for you know, x value close to 0, it's tight, right? It's close, right? You can see here. That's when you use this inequality. You use this inequality when the x value is close to 0. Okay, so now I'm going to disappear again. So let's finish this off now. So now I'm going to use this. Okay, so I'm going to set x to be minus 1 over n squared, right? X is minus 1 over n squared. Now with this x value, coming back to my probability expression above here, the probability of error is bounded above by 1 plus x to the power t, right? When x is minus 1 over n squared. Now I use the world's greatest inequality here and bound this 1 plus x by e to the x. So this is e to the x to the t, which is e to the xt. Now plug back in my x equals minus 1 over n squared here, so that I get e to the minus t over n squared. Okay, so the probability of error is upper bounded by e to the minus t over n squared. And now, if you recall, I wanted to make this quantity 1 over e to the n. So what t value should I pick to make this 1 over e to the n? I should pick t to be. T equals n cubed will give us probability of error bounded by e to the n cubed over n squared. And that's 1 over e to the n. All right, so that's it. All right, so that's the boosting phase and the world's greatest inequality. Very useful in situations where you see like a probability of error, some expression like this, where it's like 1 minus something to the power t or 1 plus something to the power something. In those kinds of situations, you know, this inequality is usually very, very useful. The last thing I'll say is that basically, you know, we have a polynomial time algorithm that solves the min-cut problem with probability 1 minus 1 over e to the n. Now, theoretically, this is it's not equal to 1, but, you know, practically, come on, this is 1, right? And the boosting, the other important thing I should say here is that the boosting is not specific to min-cut algorithm, okay? This is a common trick, right? So you can boost Monte Carlo algorithms via repeated, you know, trials. And yeah, we'll see more examples of this. You can see it in the notes and in the recitation, but this is a very common trick. Okay.